Hi, I'm Kramer Straub, and thank you for taking the time to watch my talk about HCAPP Scalable Power Control for Heterogeneous 2.5D Integrated Systems. This work was done as part of the Darker group at UC Davis. So a quick summary, 2.5D systems are limited by the package pins, and most of these pins are used for power. So by using these pins more efficiently, we will be able to enable higher performance, because it turns out they're actually rather underutilized. That's what HCAPP seeks to do by ensuring a maximum power and holding that power limit, but using decoupled control in order to retain the scalability and modularity of these 2.5D systems. And through this, we're able to get 21% to 43% geomean speed up over two different time constraints. Now let's dive right in. So some quick background, these next-gen computation speedups that we want to get in hardware really require some sort of specialization. We've seen GPUs increasingly applied, accelerators are becoming more and more commonplace. And one way to add these in more regularly is 2.5D integration. This is a technique where there's a shared silicon interposer and then specialized dies are added on top, which allows the systems to become generally larger. Unfortunately, as you do 2.5D integration, everything still shares a single package and thus a single set of package pins. Now, you want more and more IOs and more power pins. The power pins are the ones you really must supply though, and the package itself isn't scaling as fast as our demand. So, with these, if we want to maximize the utilization of those power pins, we have to think about the power behavior. Power is very bursty, as we'll see in a second. So the technique for keeping the power below the limit is called power capping. So here's a LU decomposition on a GPU. And you can see that the maximum power is almost 4 times the average power. And it decreases, so you're really paying that top cost because you have to provision everything for that worst case power. So this leads into the power limit specification, and that means that you have a power limit level of, say, 50 watts, and then a time window over which it must be kept, because you're going to naturally spike above and below, but it's sort of where that window is. And two sample windows for this would be 20 microseconds for the package pins, or around 1 millisecond for an external voltage regulator. So what exists today? There's centralized controllers such as RAPL and Turbo Boost from Intel, and we'll get into those in a second. Software-based controls, such as the ones listed here, just operate too slow for these faster power limits, and we'll provide some context later for exactly how that works out. Similarly, there's been work in heterogeneous systems, but that's all been focused on saving energy, or has been software-based, which is again too slow. So when we look at centralized controller-based schemes like RAPL and Turbo Boost, we really need to think about how SoCs, especially with 2.5D integration, have many, many components. They have, over 5,000 cores in the V100. And this means that if you have one centralized controller, you need to send all the information across those into that one controller. And this requires either global wires, which has area overheads, or a bus, which causes congestion. It's just a very difficult problem. But this isn't the only problem, because with 2.5D integration especially, you're going to have many different components. And you're going to be swapping them in and out, CPUs, GPUs, different types of accelerators, FPGAs. And it's really hard to create one central power algorithm that can handle all possible combinations. Even balancing for a single design with specific known accelerators becomes difficult. So now that let's just sort of restate our problem. How do we take that bursty power and turn it into some better performance by raising the average, capping the peak to ensure the power limit, and pushing the power to the components that really need it. But we have to make sure that however we design it, it doesn't limit the scalability or the heterogeneity of the system. We still want to be able to add in all those different dies and get that specialized speed up. And this is sort of the goal of HCAPP, or Heterogeneous Constant Average Power Processing. So before we dive into the design, let's look at, make sort of a scorecard. Here are the really requirements we have. It has to be scalable. It has to support the multiple architectures so we can switch those dies around. It has to maintain the power limit. It has to use extra average power. We're trying to use power to speed it up, and it has to react fast enough in order to hold those smaller time windows. And this is the design of HCAPP. So first, there's the core areas of HCAPP are all these colored boxes, and let's step through them. So first, there's the global controller, and this uses the control of the voltage at the global level in order to maintain the power limit. So it's sensing the current, setting the global voltage in order to push everything else down on its VF curves if it has that, or down in power overall by reducing the voltage. Then there's the domain controllers, and these are die-specific controllers that really seek to scale the voltage down based on, maybe the top voltage for the CPU is 1 volt and for the accelerator it's 0.8. Those need to be scaled to account for that. And then we also put a software interface register here in order to indicate priority. Maybe if I know that what I'm doing is key, the CPU is the key part of it, I can give it more priority and derate the others. Then there's the local controller. This is where you can use the local metrics right by that component to maximize its efficiency. If something is operating at its peak capability, I really want it to try and go as fast as possible, and that's what the design does. And if it's operating lower, then it can go slower. And the reason this is right down at each component is that these metrics are inherent to the component. So for a core, it might be IPC. For an accelerator, it might be an input FIFO occupancy. There's a lot of options here. So with that in mind, the best way to really understand it is to sort of step through the behavior itself and see how it all reacts. So the first part of this would be an activity change. I picked a compute unit here, and let's say it increased its power. From there, that increased power draw would propagate back to the global VR, which would then sense it. It would feed that sense value into the global controller, which uses a PID controller to determine the next voltage. It sets that voltage to the global VR, and that settles. Then that new voltage would propagate back to the domain VR, which would sense it, and then feed that to the domain controller, which uses the priority and the new sensed domain voltage in order to assign a new domain voltage. From there, that propagates down to each component, and then that local controller will then set the local voltage based on the metrics itself. So taking metrics from the compute unit, maybe how fast, how efficiently it's operating. And then at the final stage, you have a new local voltage frequency pair assigned to it that is maintaining the power limit. So I mentioned a PID controller for the global controller. One of the key things, what is that? I put an equation here at the bottom. If you're not familiar with them, they're very powerful general purpose formulas in order to control sort of unknown systems. But the key part to them is the tuning. And we do this with a simple methodology. First, we increase the proportional component, the Kp here, until the system starts to become unstable, while all other constants are 0, Ki and Kd. Then we would increase the integral component, Ki, until the steady state is acceptable. And we actually found that we don't need the derivative component for this design. Then the local controllers, like I said, they're those, some of the special sauce to this. How you design them will really determine how well you can pull that efficiency out of each component. So these local controllers will use the local metrics, IPC, warp occupancy, FIFO occupancy, really anything that you think might be useful, and then you can scale that voltage locally to sort of say, hey, if something's performing efficiently, have it use as much power as it possibly can. Maybe something's operating at 50% efficiency. You don't want it to use much power in order to free that power up for the other components that really need it. And in this design, we use the high IPC controller for the CPU and the dynamic warp controller for the GPU from the CAPP and GPU CAPP works. And if you want details on those, I encourage you to go read up in those papers. And finally, we have to come back to this idea of, is it going fast enough? How long does it take? With a combination of review and simulations, we were able to determine the actual cycle time of the entire system. And from that, we found that it would be between 147 and 617 nanoseconds. From there, we took a relatively conservative step back and said 1 microsecond for the actual cycle time. So revisiting our scorecard, how did we do? Is it scalable to many components? Yes, obviously we have no global wires beyond the power supply network, which you must have, no buses, anything like that. So we know that's passed. Does it support multiple architectures? Will the domain controller and the local controller use architecture-specific information to sort of enable that? Does it maintain the power cap? Yes, that's the function of the PID controller. It's based on how you tune it. Does it use the extra average power? Yes, the PID controller is going to ensure that we increase that power or below the cap using that global controller. And is it fast enough? As we just showed, it's operating at a speed of 1 microsecond, which is definitely fast enough. So we sort of passed everything and we had to think about how to evaluate this. So we first defined a system to evaluate, which was 1 CPU, 1 GPU, and 1 SHA accelerator. We focused on how long it takes to complete a full set of work where we're kicking off one benchmark on each component in the system, each domain, the CPU, the GPU, and the accelerator, at the same time. And we made some novel combinations of those benchmarks based on their characteristics. So the CPU we modeled using the Sniper simulator with the McPat power model. The GPU we modeled using the GPGPU simulator, GPGPU sim, with GPU watch for the power model, and the accelerator was modeled using an analytical model based on the Suresh et al. Paper of an SHA accelerator. For the benchmarks themselves, the work that is being done, the CPU we use the Parsec benchmark suite, the GPU we use the Rodinia benchmark suite, and the SHA accelerator used an analytical model. And what we did was we took these benchmarks and we categorized them. We took a subset based on their power behaviors and mixed them up. So we would have one that is low power and low power on the CPU and GPU. And maybe high power and high power for the CPU and GPU. And all these combinations are explained in a bit more detail in the paper. So finally, we needed some comparison systems. So the most basic comparison system was a fixed global voltage system. So that's saying, everything's operating at the same voltage. Then we have the HCAPP at the 1 microsecond control period. This is how HCAPP would functionally work. Then there's HCAPP at 100 microseconds. We think of this as a RAPL equivalent because that's roughly in the range of where it would be able to operate. It's likely a little optimistic. And then there's also HCAPP with a 10 millisecond control period, and that's operating at the speed of a more complex software algorithm. And we defined two constraints for the system. So we said two power limits, a 100 watt 20 microsecond window power limit and a 100 watt with a 1 millisecond power window. And with all this sort of framework set up, now we could run our simulations and get the results. And let's take a look at those. So first there's the maximum power. How did they all do? Because if you don't hold the power limit, then the system will fail, as indicated by this red line. As we can see, the RAPL-like and software-like greatly exceed the power limit over this 20 microsecond time window. And across the bottom, there's the definition of all the different benchmarks combinations. The CPU and GPU obviously have power characteristics, and the accelerator is more of an analytical model. We just gave it a fixed amount of work. But as you can see, HCAPP doesn't exceed it, whereas RAPL-like and software-like do. So from those, we know that those are invalid for this 20 microsecond window. We'll come back to them with the 1 millisecond time window power limit. So how does HCAPP do? It actually gives a speed up of 21% over the fixed voltage system across the benchmarks, and you can actually see that there's a bunch of cases where, low, it's actually able to increase the voltage quite a bit and get a lot of speed up there, whereas the mid case, there's not as much opportunity to speed up. And finally, we look at the PPE, which is the provision power efficiency, and that's defined as the average power over the power limit. How efficiently are we using up all this power? And you can see that HCAPP actually uses the power up more efficiently. and we're able to use an extra 10% of the power, basically using those pins 10% more efficiently in order to get our speed ups. And since we're really seeking out from the beginning to use the pins more efficiently, this is a really good result. So now we go to the slower time window. We can see the maximum power, looking at the 1.0 line. Both RAPL and HCAPP still exceed it. The RAPL-like approach looks like it could work. It's just slightly over. Software-like, if you look at that burst is 20% over. That's a bit much to really believe it could work, unless it got extremely defensive, I guess, card banding. There are ways to make it work, but it would significantly hurt performance. So we still considered them. We basically said, take this into account, but let's look at how they perform as well. And so even with their overly aggressive power behaviors, looking at the performance, we can actually see RAPL outperforms, especially in this burst, I'll call it burst dash workload. The first workload being the burst, it actually outperforms HCAPP. And that's basically because it will sort of ride through some of these bursts and stay higher. But overall, HCAPP does outperform it. The geomean speed up for HCAPP is 43% over the fixed voltage system, whereas for the RAPL-like, it's only 36%. So we're able to outperform it. And looking at the provision power efficiency, you can see that the HCAPP is using up 93.9% of the power, which is a huge increase over this 1 millisecond, in this 1 millisecond time window over the fixed voltage, which is 69%. The RAPL-like uses 79.7%, so we're able to use that extra roughly 14% of power to translate it into an extra 7% performance. But remember that this is free power. You've already set up for it. You already have the pins there, so you're really just using everything more efficiently to really squeeze out all the power and all the performance in your design. And finally, we mentioned we had a software interface, and so we did a test to make sure that interface works and how well it works. So we said, what if I just prioritize a component? And I want to prioritize the CPU, and how much faster does the CPU go? And based on this, we can see that just prioritizing the CPU, we get an 8% speed up on the CPU. Just prioritizing the GPU, we get 5% speed up. And just prioritizing the SHA component, we get 12% speed up on the SHA accelerator. So this was really nice result to find. You can see there are actually some interesting behaviors where prioritizing a component actually makes it perform worse. These could likely be solved in the software portion, but they are very interesting results to find. So just some quick final thoughts. HCAPP is a power management architecture that can manage heterogeneous systems. It can scale up to the 2.5D integration and really handle those large systems by having decoupled control. And then we'll maximize the performance under the power limit by really utilizing the power available in the system due to the over-provisioned package power pins based on those high maxes and lower averages, kind of squeezing those together. Across two different power limits, the pin power limit of 20 microseconds and the VR power limit of 1 millisecond, we're able to get speedups of 21% and 43% respectively, and increase the provision power efficiency by 10% and 35% respectively. So thank you for watching, taking the time to watch. Please feel free to ask questions in designated channels for the conference, and I'll be there listening, answering, and responding. Thank you very much.